But 300 years before the West even had the vocabulary for it, a man in a rain-soaked Kerala village was already doing calculus. He calculated pi to 11 decimal places using nothing but a palm leaf and a metal stylus. In the man's village, a wrong eclipse prediction could destroy an astronomer-priest standing. That pressure produced some of the most advanced mathematics the world has ever seen. This is the story of Madhava, the man who saw infinity, and there's also a story of the Kerala school of mathematics and why the world forgot it existed. The rain falls hard over 14th century Kerala. An oil lamp burns low. Madhava is awake, etching careful lines into a palm leaf with a metal stylus. Outside, the monsoon drowns every sound. Inside, a quiet revolution unfolds. One man is exploring mathematics that the rest of the world will not formally rediscover for another 300 years. He calculates pi correctly to 11 decimal places, 3.141592653539, in a small village few will ever hear of. He comes within 4 digits of the precision NASA would later use to navigate spacecrafts between planets. This is the Kerala school of mathematics and astronomy. It begets the question, why did it take so long for the world to recognize their work? In the Kerala school, mathematics was not one man's genius. It was a living tradition, teacher to student, commentary to commentary, verse to verse along the Nila River. For nearly 2 centuries, each generation carefully built upon the work done by the last. The tradition literally began with Madhava and endured long after him. Madhava's own manuscripts have almost vanished, but his ideas survive because others preserved them. And those ideas were extraordinary. Madhava showed that sine, cosine, and arctangent could be written as infinite series, adding more terms whenever greater precision was needed. This is an essential idea behind the Taylor series century before it became part of modern calculus. Madhava had reached it first in 14th century Kerala. To understand Madhava, you have to understand what drove him. Every infinite series he refined was never an academic exercise. In a temple-centered Kerala, astronomy governed ritual. A calendar that wrongly predicted an eclipse could damage a temple's authority and the standing of the Astronomer-Priests family built over generations. The same instinct that drives a modern analyst to improve a risk model drove Madhava to push trigonometric approximations further than anyone before him, not for recognition, because his family's livelihood depended on the moon appearing exactly when he predicted. The history of mathematics is rarely powered by curiosity alone. Its greatest advances often come from consequence. The Kerala school pursued precision because mistakes in the sky carried real costs. And that brings us to the document that should have changed everything. You're on India's Golden Age podcast. Subscribe now. In 1530, a scholar named Jyeshtadeva chooses to write in Malayalam instead of Sanskrit. He wants to be understood. And he also did something which was even more important. He explained the proof, the reasoning. The Yuktibhasha, meaning the language of reasoning, is not a catalogue of results. It is a book of proofs laying out the derivations behind the infinite series for sine, cosine, and arctangent, discussing methods that resemble early integration and examining the irrationality of pi. It was written for students, calendar maker, and working astronomers who needed to understand and apply the mathematics, not merely to memorize it. While Europe was more than a century away from scientific revolution, Kerala already had a proof-based mathematical text containing methods later linked to Newton and Leibniz. Now let's go back to another 30 years to around 1500 Common Era to a gentleman called Nilakantha Somayaji. More than 40 years before De Revolutionibus was published in 1543, Nilakantha had already developed a striking new planetary model. In a Tantra Sangraha, he proposes a planetary model that breaks from the familiar geocentric picture. Nilakantha's model kept the Earth at the center, but had Mercury, Venus, Mars, Jupiter, and Saturn orbiting the Sun, which in turn orbited the Earth. A partial heliocentrism. It was a model built from calculation, not from philosophy. His work goes further, presenting inductive proofs, refining the Madhava-Gregory series for arctangent, improving the computation of pi, and examining why pi can never be written as a ratio. In 1835, Charles Matthew Whish, a young Indian East Company civil servant, arrived in Kerala. He worked with Malayalam scholars to study the Tantra, Sangraha, the Yuktibhasha, the Karuna Paddhati. The mathematics astonished him. In a paper for the Royal Asiatic Society of Great Britain and Ireland, he described these works as abounding in fluxional methods and infinite series. Fluxions was Newton's own term for derivatives. Mr. Whish found himself questioning how the history of mathematics had been taught in British India, and yet little had changed. His paper was cited by the specialists, but never reshaped the books of the British Indian Empire, where generations of Indians learned that calculus began with Newton and Leibniz and nowhere else. The recognition for Kerala school came much later. From the 1940s onwards, scholars like C.T. Rajagopal, David Pingree, etc. helped restore the Kerala school to its rightful place in the history of mathematics. But this is a thought that stays with me. Every smartphone processing a sine wave, every GPS satellite calculating position, and every engineering student at IIT Madras or MIT learning numerical methods draws on ideas that can be traced back through generations of mathematicians to scholar working on a reed mat in a rain-soaked, monsoon-heavy village in Kerala 6 centuries ago. You are on India's Golden Age podcast. Share and subscribe. And to immerse yourself deeply in India's Golden Age, check out my novel Dhruva Devi, a queen who made Chandragupta, coming out September 2026. Bye for now and Jai Hind.